Good afternoon, everyone. Welcome to today's event, Next Gen Architects and Researchers, applying new methods and tools to the making of future high-density livable cities. This webinar is the second in conjunction with the Dense plus Green Cities exhibition that was shown at the National Design Center from March to July 2020 and highlights the cutting-edge methods and tools that the next generation of researchers and designers apply to inform the design of future high-density livable cities. This event is organized by the SUTD Advanced Architecture Laboratory and the Design Singapore Council and supported by the National Design Center. This event is also part of the National Design Center's Next Gen program lineup for October 2020. My name is Anjana Devi Srikanth. I'm a researcher at the SUTD Advanced Architecture Laboratory, and I will be your MC for today. Today's session explores some tools and methodologies to derive new planning and design strategies for high density and livable cities that acknowledge their scale and the complexity of the urban systems. With the help of new tools and methods, it is possible to gain insights from everyday activities on streets and public spaces. One of the tools that helps us decipher the complexity of cities better is network science. Simply put, it helps us understand our streets, public and commercial spaces in a larger scale, how connected they are, how easy it is to get from any point on the network to any other, how probable you are to take a particular route to work every day, and to understand the optimal allocation of public and commercial spaces. With the help of computational tools, it is possible to derive information from a vast amount of data about streets. This enables decision makers to optimize design strategies for accessible public spaces, better streets, and efficient transport systems. With this, I'd like to introduce our speakers for today, Srilatha Gopalakrishnan and Ajay Kumar Manivannan, who will elaborate on spatial network analysis, some of its technical aspects, and its implications on design and planning in architecture and sustainable design at SUTD Singapore. Her ongoing doctoral research interest focuses on the increased benefits of integrated landscape design on high-density urban environments and the development of strategies towards an evidence-based design practice for sustainable and resilient urban design solutions. I'd also like to introduce our other speaker for today, Ajay Kumar. Ajay graduated in 2016 with a master's degree in aerospace engineering from NTU Singapore and TUM Germany. With a specialization in urban science, Ajay's doctoral work is focused on emergent mobility patterns in vertical cities. Shri and Ajay, over to you.
Thank you, Anjana. Thank you for the introductions and also for setting the context for the presentation. Let me start by thanking Design Singapore and the National Design Center for giving us a platform to share our ongoing research work with all of you. Today, our presentation will be discussing mainly three questions. Why is it significant to explore new research methods and tools to understand the design of future high-density livable cities? How can we use these new methods that are available today for our objectives? And finally, what are we expecting to contribute for the future planning and design of cities? So let me start with the overview of why we need to explore the new methods. With 70% of the world population expected to live in urban areas in the next 30 years, future cities are going to be characterized by high densities, more complexity in terms of multiple interconnected systems, and verticality, as there would be a need to keep the built footprint compact, sustainable, and resilient. Thus, future cities we will be living are going to go dense and they're going to be vertical. Now, in addition to these two components, another third element is going to be green. So integrating intensive greenery within the urban environments have proven to be a critical factor in transforming these dense and vertical concrete jungles into high quality, livable cities. So in cities like Singapore, public and common spaces and networks on ground are increasingly complemented with such spaces and networks on elevated levels in the form of sky bridges, sky parks, sky gardens, and roof gardens. Now, combinations of these often applied to mixes of residential, commercial, civic, institutional programs combine at times to produce vertical cities where such spaces become components of a larger urban system and networks. So the dimension of verticality presents possibilities to generate dynamic urban forms and utilize cutting-edge technologies to provide new insights into addressing the environmental issues of climate change and urbanization. By challenging conventional notions of urbanism, it offers new possibilities towards reimagining cities and creating sustainable, resilient, adaptive, and responsive livable environments for the future. As you see, this imagery, which was created in 2011 by Woha as its vision for a future vertical city, we're not very far from this vision to becoming reality. So having established the need to explore new methods, let's see how can we do what we are intending to do. Now, often as a designer, a landscape architect, I've wondered how some spaces we design become highly successful and well used and become an integral part of urban life, while some spaces do not exhibit the same quality of integration in terms of its social and spatial performance. So what makes some design spaces more integrated to the larger urban network, while the others, equally well-designed spaces, fall short of expectations? So these questions become more significant as spaces need to be socially, spatially, and economically sustainable. So as cities get compact, systems get multi-layered, and spaces get interconnected at horizontal and vertical planes, there is a need to understand the complex interactions of extensions of the public and common green spaces into the vertical dimension with those on the ground, their impacts on the patterns of human movements and social interactions, their contributions to a more livable high-density urban environment, and more significantly, the scalability of these urban elements for their effective performance. So traditionally, design and planning approach has been guided by our instincts or intuitions, by our past project experiences, and a tried and tested method approach. What we need to do is to layer them with an evidence-based integrated design approach to create socially sustainable spaces that can also respond to various programming. Now, gathering evidence has also traditionally been limited to user surveys, visual observations, past studies, and guidelines. But with the advent of technology and access to a vast range of devices, new accurate methods can be applied to collect user data. So this would provide a dynamic feedback loop and enable scenario modeling for assessing spatial performance. Thus, what we need is a systematic and integrated approach towards creating physical, visual, and social continuity from the ground level horizontal urbanity to its vertical urban extensions. In a recently completed study on dense and green building typologies by the Singapore ETH Center Future Cities Laboratory, the integrated vertical developments were systematically analyzed for their larger urban impacts. And the study successfully concluded that these new integrated typologies become an integral part of the larger urban ecosystem and are also very effective in providing the ecosystem services. More importantly, the benefits can significantly multiply with its effective social and spatial connectivity with the larger urban network. Thus, understanding the interconnectivity of the spatial and social behaviors is imperative towards planning future urban environments. Now, urban network studies have been carried out for many decades now to understand spaces from the way people move through them. Academics, architects, planners, and designers have widely used the tools and concepts of space syntax to understand the configurations of spatial layouts and the relationship between the spaces. A wide range of tools have been developed and explored, and they have been pretty effective in understanding built spatial networks. Complexity science, with its evolutionary approach, looks at networks as a generic system of nodes and edges. that constantly change and evolve with an underlying structure that has a pattern and that can be generative. So, with cities becoming more complex and urban systems becoming multi layered and interconnected, application of complexity science in understanding cities and urban systems is slowly gaining momentum. Thus, the application of complexity science methods present a new scientific approach for designing and planning future cities. I would now take the opportunity to hand over the presentation to Ajay, who will give us more insights on how this approach becomes an immense potential for future architects and designers. Over to you, Ajay.
Thank you, Sri. Yep. As Sri mentioned, that the contemporary urban design is actually primarily driven by intuition and heuristic methods. So every year, more people move to urban areas in record scale, and cities have grown dense and vertical to accommodate this trend. So this increasing density has encouraged cities like Singapore to design vertically integrated developments that consist of hospitals, supermarkets, public transportation, shopping complexes, restaurants, parks, and other community facilities in a single building. So in this presentation, I will try to answer some important questions on the future of high density urban design process. As a start, we can actually confidently say that it is going to be interdisciplinary and it will be informed by the recent developments in science and technology. First, we'll actually talk about how science can help. Complexity science is the study of complex systems. There is no agreed upon definition of what a complex system is, but it does have some distinct properties. A complex systems consists of individual components that actually interacts with each other to create a collective behavior that is greater than the sum of its parts. It is dynamic, it is unpredictable, it is non-linear, and it can be very difficult to model. So, but why do simple individual components give rise to complexity during interaction? It is not always clear, but unless you actually understand that the interaction itself has weights, and the type of interaction that is actually possible can be larger than the size of the system itself. So some examples of the complex systems or the Earth's climate system, the natural ecosystems, and even an ant colony is a complex system. Now, the two complex systems we are going to actually explore are the cities and the human society. So it is recently postulated that there is a direct connection between the structure and organization of a city to the our structure and organization of our social networks. So the city is the people. So the subfield of complexity science that studies the interaction between these two complex systems, humans and built environment, is the urban complexity. So the field of urban complexity has three important factors that reveal the interaction between the inhabitants and the built environment. The human mobility, the co-presence of people, and the spatial configurations of the city. The network science is another field of complexity science that allows you to represent the system you're studying as networks with nodes representing individual components and edges representing the relationship between them. The built environment can be represented as a spatial network, and the human interaction in space can be represented as a co-presence network. Both human mobility and co-presence can be considered as a dynamical process that actually takes place on a spatial network. Now, there are two important field of metrics to study urban complexity. One is the socio-spatial network properties, and the statistical properties of mobility, co-presence, and spatial network. So on the socio-spatial network properties, we have the node properties, such as the centrality measures, that defines the importance of a node based on a criteria. For example, between a centrality says which node in a spatial network is best placed to allow as many shortest path as possible through them. So if a particular location in an integrated development, say, is said to have the highest between a centrality, it means that it is the best place to start to reach any place in the building with minimum travel distance. And the degree of a node defines the number of connections you have in a social or a spatial network. And finally, the clustering coefficient tells you how many of your friends are actually friends with each other. In a spatial network, it tells the interconnectedness between a node's neighbor. The edge properties like shortest path tells you the shortest distance between any two nodes. And overall, a network can be actually defined by an average clustering coefficient and an average shortest path. So this global properties allows you to compare two different networks. For example, you can compare an integrated development with an area that is distributed on the ground horizontally with similar facilities. And you can also compare two buildings and evaluate which fosters better connectivity and has optimal allocation of facilities. So we can also assign attributes to these networks that are actually useful for a richer evaluation. For example, in node attributes of spatial networks, we can define the size of the area. Does it have benches? Does it have garden? We can also assign the type of location. Is it a social space? Is it a health facility? Similarly, in social network, we can actually define gender, age, income level. On the edge attributes of spatial network, we can denote the level of visibility between any two nodes, the routing distance between them. We can also use the mobility data that actually be derived from location data like GPS or Bluetooth, and represent it as an amount of traffic that actually takes place on the spatial network. So similarly, in actually in a co-presence network, we can give the amount of time two people spend together, how many and the number of times they have spent together. So next, in the statistical properties, we have two important metrics. First is the scaling laws, and the second is the probability distribution. Now, the scaling laws actually reveal the relationship between two or more parameters. It actually shows how one parameter scales with the change in another parameter. So these parameters are actually based on real world data. For example, the graph on the left here shows how the crime rate, the GDP, the income and patterns in 360 US cities scales with the increase in population. Both the axes here are actually in logarithmic scales. It shows that for every percentage increase in population, we have a 15% increase in GDP, income, and patterns. But at the same time, we also have the same amount of increase in the crime rate. So similarly, for every percentage increase in population, we also have a 15% increase in number of social connection that is formed in a city. Now, any complex adaptive systems can actually die. The rise and fall of many companies can actually be attributed to its failure to not innovate exponentially to keep up with its growth. So similarly, the life and growth of a city depends on its ability to be a facilitator for social interaction. And the best way to make sure is to design our cities and its built environment to maximize the chances of social interactions. So another statistical property is the probability distribution. So the data from human mobility, which is the displacement in space, can be aggregated and represented in probability distribution. For example, this graph reveals the probability of each order of displacement in space. As you can see, the long travel distances are less probable to occur, while shorter distances are the most probable. Now, besides pointing this obvious fact, the probability distributions can be actually very powerful. The shape of this distribution of displacement can actually reveal characteristic features of a particular building, a location, or even a city. So similarly, in a co-presence network, the duration of co-presence between all pairs of people in a network can be represented as probability distribution. All co-presence events in a particular location can be aggregated as probability distribution. So hence, each location can actually reveal its ability to facilitate social interactions. So how do we make use of these metrics in urban design. Now, the socio-spatial network properties allows us to define features of a location, uh, define characteristic features of a location. For example, by actually having a defined social metric, connectivity metric, and space use. And the scaling laws actually allow us to predict several socio-economic attributes of a city. For example, how much infrastructure is required if for a particular order of increase in population. And finally, the probability distribution that we just saw, for example, for mobility in a building or a city, can be used to make very accurate agent-based models. And it also can help us find optimal allocations of facilities. So we have so far seen how science can actually help us with informed design. Now we will actually see how recent advancements in engineering and technology can actually help us understand the science of urban complexity. So the sensors, or a collection of sensors, connected sensors, form the so-called Internet of Things, which is a key to actually studying complex systems that act like cities that actually requires large scale collection of data. So at each step of this process, machine learning can be used to learn, predict, and optimize this system. For example, at the sensor level, machine learning can be used to detect any anomaly in the sensor data, or the health of the sensor itself. And it can be used to assign adaptive sampling rate to actually optimize energy consumption of the devices. And at the collective level, the machine learning can be used to optimize sensor fusion of the different sensor data. And finally, the big data that we collected can be actually used to track several human activities. For example, like is a person walking, running, or they on a transportation mode. And it can also actually track the social behavior of people. Now, these in turn can be used to expand the already current knowledge we have and actually inform the science of urban complexity. If we leverage this right, it can also be used to make informed urban design. Now, some examples of how different sensor can be used to track human activities are actually shown here. For example, Bluetooth can be used for localization and tracking. And a Bluetooth or a Wi-Fi or a radio frequency identification device can actually detect when two people has been actually co-present together. And barometers are actually very generally used to track vertical mobility, and accelerometer signals can actually be used to detect body movements. For example, a person is sitting, running, or actually standing. So to conclude, the subfield of the complexity science that we have seen so far that deals with the cities is the so-called urban complexity. It tries to actually understand the human behavior and the built environment and the interplay between them. And the network science has another subfield of complexity science, allows us to actually build network representation of this human society and built environment. So this socio-spatial network and their statistical properties allows us to understand mobility, co-presence, and the spatial configuration. So this in turn, we can actually use that to actually make very informed decisions on how to design future high-density livable cities. We've also seen what are the recent advancements in technologies and how we can actually help us to collect data that also improves how we understand the science of urban complexity. So, and these advancements, they are not they are just to be applied at city scale to build better cities, but we can also build better microcosms of cities like the integrated developments. So thank you. Now I will hand it over to Sri to explain our future works and application.
Thank you, Ajay. So that was kind of a prelude to what what opportunities this new field of study provides us with. So acknowledging the adaptive potential of complexity science for future cities planning, complex system studies has been recognized as a key research track under the Ministry of National Development's Cities of Tomorrow R&D program here in Singapore. As part of a larger study, SUTD is currently working in close collaboration with the Urban Redevelopment Authority, the Center for Livable Cities, and Housing Development Board on a pilot study at Kampong Admiralty to test the new scientific methods and tools for understanding the urban networks for planning future cities. So the project will explore the vertical integrated networks within the built space in its vertical distribution and its relationship with the larger urban fabric. The methods will analyze the spatial networks for their interactions, for their structure, the centrality measures, the degree distributions, the connectivity at urban scale, in addition to integrating actual user data to generate co-presence networks, socio-spatial performance of the urban networks, and the active space use of design spaces. So finally, what do we hope to contribute or achieve out of this exploration? An evidence-based, multidisciplinary integrated design approach to analyze existing developments for their performance and to effectively guide future developments for better urban integration, and to establish an effective complexity science-based applicable design approach to plan future cities that are sustainable, resilient, adaptive, responsive, and most importantly, livable environments. Thank you.
Thank you, Shri and Ajay, for introducing us to spatial network analysis. It's interesting to understand how this can be used as a tool in the design community to understand how we are currently designing spaces and how to inform us better for future projects. So right now we move to the panel discussion and the Q&A segment. Before we start the Q&A segment, I'd like to mention that during the webinar, we polled 2 questions. The first one being, how critical would interdisciplinary collaboration be for future design of cities? For which a significant majority of those who voted said that it's very significant. And the second question being, should future designers and architects seek to gain multidisciplinary skills, or would the better solution be to have an interdisciplinary team of scientists, architects, and other professionals on board, which would be more ideal? In this case, a majority of you, around 60% of those who voted, have said that it depends on the complexity of projects, which is a very nuanced take on what we are also trying to talk about and the methodology. So I'd just like to point out that we do welcome all your questions, but given the time constraint, all the questions may not get answered during the session, and we do apologize for that. However, we will be sharing an email with the link for the recording and the speaker's responses to your queries. So stay tuned for that. So perhaps I can start the Q&A session with a question of mine for both the speakers. What are some of the advantages and disadvantages of spatial network analysis that your experience with the computational tools has shown you?
So Ajay, you want to go first?
Yeah, sure. So there is no inherent advantage or disadvantage in the spatial network analysis. It actually depends on the context. But one thing we can say is that we have to be careful how we use certain metrics that are actually available in network science. And when we actually bring it to spatial network analysis, we have to make sure what is relevant and what is not. And try not to actually make very broad conclusions. And another thing is that the spatial network analysis should always be actually supported by real world data generated by actually tracking human activities. Thank you.
I think for me, the key aspect of this whole process is how do you bridge the gap of applying what network science provides us an opportunity with towards actually designing spaces, right? How do you bridge that gap? Like, there is potential for this, but you need to know how to apply them in real world design, right? So what we need to be careful is that some of these measures, what they kind of come out with as part of the analysis, cannot be taken in a very generic way, right? You need to kind of assess what do they really imply and what are you exactly trying to find out, right? A simple example is that maybe a certain network tells you, oh, this is going to be the shortest path and this is going to have a lot of flow of movements, right? And I might think, oh, if it passes through some of these key landscape spaces, that means my space will be very well used. But it may not necessarily be that direct a relation, right? It could be that there are a lot of people who are moving through that space, but that may also deter people from using it, right? So there is something which we need to be very careful about, is interpreting this data which we are able to extract, and making sure that we provide ample weightages, right, to whether it's the spatial quality, whether it's connectivity, whether it's visual access. There might be so many factors which influence the space use. So for me as a designer, I would be very careful in how do I extract this data to make sure I embed it in space and see how it gives me cues on designing spaces for future. Yeah.
Yeah, that's a very interesting take from both of you. We have a question from the audience. This is for Ajay. Could you please elaborate on the definition of social connectivity, and is it based on the degree of social interactions?
Yeah. So the social network actually can be constructed based on different elements. For example, you can use Facebook, Twitter, the who you message. But in this particular context that we actually looked at in this presentation, we are talking about co-presence network, which is also a form of social network. Is when two people have actually come together and been and shared a common space. So if they are sharing a common space, will be these people will be the nodes, and since they are co-present, will be forming an edge with each other. Now, this is what we call as the social connection. And the question is it based on the degree of social interactions? Yes, it is. For example, we can actually assign weights to these edges. For example, how many number of times have they been together? And we can also assign another weight called duration, which is how much time they have actually spent with each other. And this can also be a temporal edge, which means it only happens at that instant. Or we can also assign, we can also aggregate these results and say for a particular period of time, for example, over a day, these many times they have met, this is the amount of time they have spent. Thank you.
So we have another question for both the speakers. How do these methods differ from what architects and researchers did in the past?
Okay, so let me go first. I think for me personally, it's about trying to explore something which is not necessarily embedded in space, like because complexity science or this whole field of urban complexity is looking at extracting certain performance or parameters or certain ways of understanding networks, and being able to apply it into the realm of planning, right? And that has not yet been very successfully translated. While there have been many studies which researchers are still doing and architects are exploring, there is still very limited application. So for me, that would be the key part where you're able to leverage on new technologies, new possibilities, and more importantly, be able to use real data, which can be more accurate towards understanding the spatial performance. Because in the past, we architects have always relied on surveys, visual observations, which there is always a level of error margins or inaccuracies which comes in. So you have to kind of use a very large set of data to be able to come out with some kind of validity, right, of your result. However, I think with this new technology, even if we have a small data set, right, as long as we are able to relate it with that particular space and we are able to relate it with the network, it can give us a more conclusive evidence of what the patterns are or what kind of results could be derived out of it. I think that brings a very important aspect into this whole study.
Yeah. So, so I cannot actually speak for architects, but as an engineer, before complex systems, there was this idea called a reductionist approach towards actually studying systems. We actually study individual components, uh, but as the dawn of this 17th century, we are actually seeing a lot of research that has been done on complex systems. So we actually give more weight to the interactions and how they all come together than we actually give to the individual components. So that is something that has actually changed and should actually have an impact on future designs.
Thank you for that. We have a couple more questions. Okay, so this is another question for both of you. Any interesting finds so far from this research that is different from your previous design experience or technical experience?
Okay, again, maybe Ajay, I'll just go first. As I said, we are still in a very preliminary stage, and we are not at a position to share a lot of this data because it's still in various stages of evaluation. But one interesting aspect when we were looking at this was like when I looked at something which is connectivity from, say, a visual perspective, like you look at those spaces from a visual connectivity perspective, and then you look at the same set of spaces from its physical connectivity, right? The results were quite interesting. I mean, the way sometimes you feel that the spaces which are most physically connected, right, are not necessarily the most visually connected. And often the visually connected space may not be designed for a high social use. You know, it might be designed for a limited access, for a more restricted space use. So that kind of gave a very interesting insight into the way these spaces are designed in a building, right? And the question which I started off with was whether when we design spaces, why is it that some spaces perform well while some spaces kind of perform below expectations, right? So maybe there is this interesting way of looking at things, like maybe a space with high visual connectivity with also is in the path of high physical connectivity might become more effective as a social space as compared to something which is less visually connected, right? So again, at the same time, as I mentioned, we have to be very careful not to come up with a generic outcome of this, but relating it to a specific project or a specific development, it kind of gives us a good gauge to evaluate the different spaces, you know, for its space use, primarily space use with respect to the way people move through them. So, I mean, that seems to be some of these key insights. There are many more, but as I said, we are still in the process of understanding these results, and it'll be very premature for us to come up with some statements because there are many components attached to each of these, right? So I will kind of keep it at that. Yeah.
Yeah. So, so I do not actually have any previous design experience, but we're not at actually liberty to actually share more of the results. But what we can say is that some initial preliminary results that we have from spatial network analysis is actually affirms some of the validates some of the design intuitions of architects. Yeah.
Yeah.
Thank you.
So I guess I could sort of relate your answers to a question of my own, which would be that 2020 with the pandemic has shown us the dire need for good access to open public spaces. So how do you envision the future of high density focused urban design and planning with spatial network analysis and mobility based solutions?
Um, I would say, like, more importantly, as I initially mentioned, increasingly, right, space is going to become a very, very precious commodity, right? In Singapore specifically, where land is really, really scarce. And there is this increasing impact on, using natural or open systems for more built environment, right? So there is going to be this shift from trying to conserve and preserve the natural ecosystems and trying to make the existing built systems more effective or more efficient, right? So I think this whole idea of spatial network analysis is good from this perspective, that it addresses um, uh, the spatial configurations, but it also touches upon the social aspect of it. That means, as Ajay mentioned, for cities to work and to be successful, it is very important to build spaces that are socially interactive, right? That can initiate more social interactions. So for us to know what kind of spaces will work best as social interactions, right? Or what kind of spaces will discourage more social interaction. So if we can kind of narrow down those parameters, right? What are the key influencers? Is it distance? Is it the spatial attributes? Is it the positioning, whether it should be on which level? That kind of dictates whether you would interact in that space or not, whether you would go to that space or not. So all these could be understood by just being able to break down the way people move in the spaces, right? So it's an interesting possibility which opens up. And if we are able to successfully leverage on the rich insights which it can provide, and we are able to translate them into qualitative parameters, right, to designing future spaces. I think this whole question which I started with about whether the design space I'm designing is going to be effective, is it going to be integrated? It won't become a chance. It would become an intent, right? I will design with a clear intent to know that it is going to perform, right? I won't leave it to chance. I think that is where it becomes important, because we won't have the luxury to leave it to chance anymore.
So speaking of well-designed spaces, this question's both of you. Are any spaces in Singapore in particular that you really appreciate?
I think there's one picture which I already showed, which personally is something I really like going, even though it is not really close to my house. It's Marina Barrage. I mean, the fact that something which is as simple as just a set of, they're just nothing but just pumps, and how something which is as engineered and as mechanical as that could translate into an actively integrated public open space, that tells you the opportunity every project provides you with. It's just a matter of being able to tap into the right measures, parameters to make them work successfully. So personally, I keep always that as a very interesting example, when something which you don't anticipate to become so powerful can become a powerful image. Yeah, I mean, that's my personal favorite. Of course, Ajay may have his own personal favorites.
I actually like the entire campus of NTU, which I think is actually designed very well. A lot of green spaces with a lot of spaces. So.
Yeah, and also to do with land-scarce Singapore and the concept of density. So there are various different benefits of high-density cities, including environmental, social, economic, aesthetic as well, as many designers and planners know. So do some of these needs sometimes compete with each other? How should planners and designers deal with these competing needs? And how do these computational tools become part of it?
I think I can address the part about whether they compete or not. I think at some point one needs to kind of be very clear what kind of spaces are going to prioritize what kind of benefits, right? So in terms of moving forward, I would say the ground level networks, right, which are going to be extremely critical to provide the ecosystem services, right? The sense like you need to prioritize ecology, you need to prioritize the green blue infrastructure at the ground level. So that means that potentially the other benefits which we want to achieve could be tapped in on the elevated network, right? So maybe every elevated space which we design needs to make sure that they perform well socially, That means you are kind of making sure that people are using those spaces. It's being leveraged on well, right? While the ground level gets freed up to make sure that the ecological systems are kept in check and balance, right? So for me, I think that is where it will become critical in future. And that's why understanding the social performance of these spaces becomes important as a designer.
Yeah. So the parameters actually mentioned over here, environmental, social, economic, and aesthetic, all of these parameters are actually very important. So from technical standpoint, what I see is an optimization problem. Um, so before we actually optimize, we need to understand how these parameters are related to each other. For example, the scaling laws can actually say what happens if you increase the um, uh, garbage cans in the city. How does it affect things like that? We need to understand how these parameters are first related to each other, and we can actually implement optimization procedures to actually um, to make actually informed designs.
Thank you, Shri and Ajay. And with that, we've come to the end of our session. I hope you've all gained some interesting insights from the presentations. And before we leave, we would appreciate it if you could take some time to share your feedback on the session through a quick survey by scanning the QR code that's going to come up on the left of your page. A link to the survey can also be found in the Zoom chat. Please note that the survey awards 1 CPD point to SILA members. If you'd also like to find out more about programs that the National Design Center has lined up for October under the theme of Next Gen, scan the QR code that you see on the right. I'd like to thank our speakers, Shri and Ajay, for taking the time to present to us today. We'd also like to thank SUTD and the professors leading the research, Professor Thomas Schroffer, Associate Professor Roland Buffone, Associate Professor Samson Lin. We'd also like to mention our gratitude to the Urban Redevelopment Authority, the Center for Livable Cities, the Housing Development Board, and the Ministry for National Development. I'd also like to mention my thanks to Design Singapore Council and the National Design Center, and our working team who helped make today's presentation possible: Felicia, Gerald, Zed, and Janine from Design Singapore, and Daniel from SUTD. Thank you once again for spending your Tuesday afternoon with us, and we hope to see you all at the future events. Goodbye.
Thank you, Anjana.
Thank you, everybody. Thank you.